Welcome back, everybody, to the Cyberbot Robot with Python and the Microbit 3-session educator workshop. This is the March 31st, 2023 installment. If you're wanting to have a copy of the slideshow open, here are the various ways to get to it. And I will go ahead and paste into the chat the Oh, cool. So somebody said they liked the IR. Thank you. I'm glad you like it. I will be doing the IR, the infrared navigation here pretty quick. I don't know if you want to try the light following in its place if you're already done with it. Actually, I do have an Easter egg for you though, so maybe keep that IR circuit on and just be ready to ask questions. As with the first two workshops, I recommend clicking that view button, which is probably in the upper right, and selecting exit full screen so that you can put your zoom so it takes up part of the screen. And that's if you have a single screen. If you have dual monitors, set it up as you see fit. Wanted to talk a little bit about upcoming workshops. This slide's a little bit out of date, but if we follow the link that the slide goes to, you can just click the slide and a link will appear down at the bottom of the picture, or not the slide, I'm sorry, but just the picture. There'll be a link that appears down at the bottom. You can click that and end up here. So coming up on April 24th, 26th and 28th, that's another Monday, Wednesday, Friday. It's also at 3 p.m. and it says closed, Stephanie. So we're not.
Yes, that one just closed today. But if any of you are very much wanting to go and have not already signed up, like many of you have, just go ahead and email me.
Okay, great. Thank you, Stephanie. And then we also have the multi-core microcontroller activity bot that is going to be May 1st, 3rd, and 5th. That's another Monday, Wednesday, Friday, 3 p.m. Pacific time through 5 p.m. Pacific time workshop. And then after that, we have an in-person workshop in Seattle, Seattle, Washington on June 4th. And keep your eye on this page. I'll paste it in the events page because we'll be posting more workshops. We've got a number of in-person workshops that are tentatively planned for this summer, and you'll be able to see them as soon as they're finalized on this page that I just pasted in. All right, so I guess I guess this is just talking about the electronics workshop. I'm going to skip this and come back to it later. Well, aside from, I think I'll just say here that this is a view of the chapters in the electronics workshop. And there's also one on potentiometers that is not showing here. That is a mostly finished draft that is ready to get posted, or almost ready to get posted to the web. So today we'll be doing infrared navigation, talking about additional projects with the Cyberbot, as well as cybersecurity topics. We'll look at the educational resources and talk classroom implementation. Does anybody have any questions before we plow into infrared? Okay, well, if anything comes up, we've got the chat and or the any in the DC area is the question. Not that I'm aware of, but that doesn't mean there won't be any. It's just I don't know if there are any classes planned in the DC area yet. It does seem like an area we visit pretty frequently, so not out of the question for sure. I honestly don't know. Sorry. Okay.
We do have one report of an IR detector that didn't work. So maybe after you go through talking about what we did, we'll have a chance to help troubleshoot.
Yes.
Okay.
Yes. As a matter of fact, that's the first thing up, because this is one where it's at the end. It's at the end of the robotics portion of the book for the stock robot, the on its own Cyberbot. Again, the class packs have additional sensors for projects, but this is the last one in the book for the Cyberbot robot on its own. And so the students have been honing their skills in building circuits for a while now. And so this is the most complex circuit of the book. It's very easy to have a mistake and have trouble finding it. So I think it will be important, understatement. It's going to be important to see some of the thought processes in troubleshooting. The main thing is going to be just double and triple checking your wiring against the diagrams. That's the main thing. In 90% of the cases, yeah, it's more than 90%. All right, so anyway, looking at infrared navigation, the idea is that it's a lot like Whiskers, except for the robot does not have to bump into something because it's got these little infrared light emitting diode flashlights that are shining infrared light out in front of it. We can't see it, but the sensors on the robot can see their reflections. And so it sees the box, backs up, goes another way. And that particular script that it's running is actually I believe it started as the Whiskers navigation script, and we just kind of adjusted it for the infrared receivers. And then there's a higher performance one that we'll be doing too. So here is a chapter overview. And so we talk about infrared light first. And let's see, did I lose my TV remote? I did not. Good. All right. So infrared is below red, and it's out here. It's so red that the human eye cannot detect it, as opposed to ultraviolet, which is so purple that the human eye cannot detect it. And then we have the visible color spectrum in between. And so the infrared that we're using are actually, since we normally use real parts that come inside products, the real parts in the real electronic parts in this activity involve the infrared LED that's at the front of the older model TV remotes, where you actually have to point it at your television for it to see. They've been replaced with radios in many TVs these days. And then inside those older television sets, you would find a little black box that has a lens on it, and it's a black lens, and it's filtering so that it only gets infrared light. And so this part is the receiver, or the eyeball, that we're installing in the Cyberbot, and this part is the flashlight, and the eyeball will look for its reflection. Infrared remotes actually flash the light on and off at 38,000 times a second. That's 38 kilohertz. And so this has, in addition to an optical filter, that black coating on its lens, it also has an electronic filter that's looking for the light to be flashing on and off very rapidly. And what that does is it helps people turning nearby lights on and off in the room not garble the signals to the television set and have the TV set get confused and maybe think that it's getting some TV remote signals when it's not. This system also is commonly used if you go to the airport and you put your hands in front of a hand dryer or the sink faucet. It automatically turns on without you having to touch anything. These are the same parts typically that go inside there. And one thing that I like to show the students, and it really doesn't work on every phone or every document camera, but our document camera, I need to unfreeze the image. Okay, here we go. So our document camera does, so here's the infrared remote that comes with the class packs and is also sold separately. And here is the infrared LED in the infrared remote. And when I press and hold a button, hopefully you can see that. Can you see a flickering light? Okay, yeah, I'm getting some thumbs up. So the kids think this is pretty interesting because if you just kind of look at if you just look at this light as you're pressing the button, there's nothing visible because it's not visible to the human eye. All right. And for those of you, iPhones typically filter pretty aggressively on the infrared. So if you look at it through an iPhone camera, you're likely not to see it. But Androids, a lot of Android phones do allow you to see it. I know my Samsung Galaxy does. And we have some pictures in the book. I'm currently in the web book, by the way. Going to the next page. This is where your homework was. And so we gathered all these parts and we made sure to get the infrared light emitting diode that had the very dome-like look to it, as opposed to the flatter top photo transistor that's used for light detection. Then we put it in this, we put the two infrared light emitting diodes into two little cases. This lower part is called an infrared standoff, and then the upper part is called it's called the LED standoff and the LED shield. And basically it just makes sure that light comes out the front as opposed to in all directions. And then we built the circuit. And so this circuit, how many folks had the tests pass? Looking good, Dennis. And Dennis Dennis didn't get all his infrared receivers. So he has a modified circuit that looks perfect, Dennis. Did it test out okay? Oh, excellent. Fantastic. All right. So I did not see as many thumbs up as I'd hoped. So, okay, there's one more. Okay, we're seeing more. Good. Oh, looking great, Kathy. Excellent, Kate. Okay, so would anybody like to talk about one where they couldn't get it working?
I had to adjust some of the timings to make it go backwards a little longer, but other than that.
Oh, it didn't back up far enough. That's right. That's the same adjustments that we had to make on the whiskers. We should really change that in the book. I like the students to start with something that works pretty well so that there's enthusiasm. I mean, true, they have been tinkering for a while, so maybe they'll take the same approach you did, Dennis. Yeah, let's talk about that, Stephanie.
There's also, Rachel had difficulties. I think one of her IRs or receivers didn't work.
Okay.
And she is asking about navigation with just one. I know there was an alternative way to do that.
Yes, it does work. But let's first look at troubleshooting the infrared receiver.
She mentioned things getting hot.
Well,
So-
yeah, if the receiver got hot, it might now not be working. That's true.
Mhm.
Let's see. Let me just check my email off screen here, and I'll see if I can find the email I sent to Dennis because Dennis only received one infrared receiver. There's the email. Just a second. I'm pulling up the okay. So.
And then this one will work because it knows which IR emitter is emitting when it sees a reflection, correct?
Yeah, you don't even need to change the code. Well, I mean, Dennis changed the code for performance reasons. But this is a way to do it. You basically leave each infrared light emitting diode where it is. And then you pluck out both of the infrared receivers. There's one right in this area and then another right here. And then what you do is basically plug the remaining good one in the middle. And by the way, Rachel, we can send you another receiver. Just send us an email reminder and we'll get you, we'll send out a couple just to make sure that you have it working. So So then put the one good receiver in the middle of the board. Run the red wire from one of the 5V sockets to the topmost of the 3 wires, and that's with the lens pointing this way. Then run a black wire from a GND socket to the center lead of the infrared receiver. And then the two resistors that were connected to the infrared receivers to begin with, leave them in the same sockets they're in over here, and just unplug them from their sockets over here and plug both of their ends into the bottommost pin, the same row of 5 as the bottommost pin of the receiver. I'm trying to think of how to make this persist while we continue. Stephanie, any chance you could email Rachel a picture of this if I forward it to you?
Yes.
Okay, thank you. Forward. Okay, I think that should come through with the attachment. Let me know if it doesn't. But in summary, it's the same circuit, just with the 2 infrared receivers disconnected, and then the remaining good one plugged in the middle with 5 volts connected to the top pin, GND connected to the middle pin, and then the two red, brown 220 ohm resistors connected to the bottom pin, and that's with the lens looking this way. The little bump is facing forward, not to the back. All right. So I'll assume then that we're all tested and ready to go, and do stop me if you need help, any additional help troubleshooting. Then we can test the infrared objects and detectors.
Oh, hey, Andy.
Yes.
I'm wondering if who was it? Was it Katie? Someone said that there was actually getting warm. If the blue wires were missing that go to ground, would that cause that problem? Because the blue wires are in the graphic and in the diagram, but they're not listed initially when it says gather these materials.
It just says miscellaneous. We didn't specify how many.
Oh, got it.
So,
Got
but
it.
I can see how that wasn't specific.
Yeah, but if the blue wires were missing, would that cause?
Not
Sure.
to my knowledge. I mean, I could try it, I guess. But I don't think that just not having a ground wire is gonna be enough. Usually it's getting the ground and 5-volt supply wires swapped.
And
Is
those blue wires are connected to the IR LEDs and not the receivers. So I don't see how that would make the receiver warm.
Oh, okay.
yeah, but if for example, yeah, it's pretty easy to make a wiring mistake where you end up swapping the red and black wires on the receivers. So these 2 rows right here. And that, I think, is what heats it up. It's been a long time since I've had one heat up on me, so I apologize. I don't remember exactly how to make it happen. But I guess it can happen since it just happened to one of us. So yeah, and then possibly we could do a follow-up Zoom with anybody who had one heat up, because it may have survived it. Of course, it may not have. And I guess this would be a good time to mention that you can get spare parts. So if you go to www.parallax.com and you can type small robot into the search field, And then, so here's the hardware, small robot hardware refresher pack. I'll copy this link. And paste it in. So that's mainly the nuts and bolts. And pardon me while I find the chat. Okay, so there's that package. And then this is the small robot electronics pack. I'll paste that in. It's nice to have a few extras of those for when these kind of things happen. And then there also, you'll see things like the tail wheel ball, a wheel, a whisker. There's lots of things in the small robot category that can serve as replacement parts. A battery pack. Buy servos on their own. And there are a few things that actually don't apply, but a search for small robot usually gets you, at least on the first page, those 2 bags of parts. So here is like an individual infrared receiver. All right, so so there we go on replacement parts. And the next up that you did for the homework was testing the infrared receivers. And so this test, I'll go ahead and paste in, and let's all just rerun the test to make sure we're okay with it. That'll be a good exercise to make sure that you have connected your microbit and plugged in the batteries, and that you have a template open, or if you just want to reopen, if you saved your work, that's ideal because you can reopen your infrared test. So let's see here. Oh, went to V3. There's V2. And go ahead and grab this code. I did already paste it in the chat. Okay, and so first of all, I'll hit load save, and then or browse for file to open something. And I'm looking in my downloads for Cyberbot template. And then once that's opened up, I can go ahead and paste in the test code and connect, flash. And then we'll be taking a look at the Cyberbot here. Okay, so when I set the power switch to 1. Man, I always seem to have trouble with lopsided stuff here. I had that servo motor that wasn't running the other day, and now I'm not getting a light on with P21. See the, where is my pointer? Yeah, so my P21 light is staying off, like it's always seeing something. And my P20 light is on like it should be. So the P20 light is going to be the left IR receiver. And so if I put my hand in front of the left IR receiver, it goes out, then it comes back on. And now looking at the right IR receiver, it's not behaving properly at all.
It's because we're watching.
Yes, it is, of course. Well, I mean, this is good because it's troubleshooting 101 here. And this will undoubtedly happen to some of your students. So Guess I'll look at the script first and make sure, it's because that silly student wasn't paying close enough attention. They expected both of them to come on and off when this is only testing the left infrared receiver. And for the homework, we scrolled to the bottom. So in the activity, the students, they run the working code to test the left IR receiver. And then it's up to them to modify it to test the right IR receiver with some hints in the red checklist instructions. And then at the end, we test them both together. Okay, so I'm going to paste that one in. And okay, so there it is for you all in the chat. And when we go ahead and flash that, mine was flickering until I moved some stuff off in the distance out of the way. And so here we are. And if we take our Cyberbot box and insert it towards the right sensor, now the right sensor is off. And then keep going. And when it gets in front of the left sensor, the left light turns off. And then as it passes by, goes away from the right sensor, the right light, the P21 light turns on. Then if I keep moving the box out of the way, the P20 light, the left light for the left sensor turns on. So we want to make sure that everybody has that behavior. And even if you're using that alternate circuit that I sent out, where you're using a single infrared receiver, this should still work just fine. Okay, I see a question. Have you considered a lithium ion pack for the Cyberbot? No, what we have is what we have in our kits is a nickel metal hydride set up instead.
In the
I'm-
12 packs. I can pull that up for you.
Okay, well, I think it's good to show it.
Okay.
So, but instead of the 12,
Just search Tenergy if you want.
you remember if Tenergy has 1 or 2 ends?
One.
Okay. Well, it found it anyway. That's good. All right. So here's the Tenergy batteries and the Tenergy charger. So you get a 12 pack of batteries. That's enough for 2 robots plus a couple spare batteries. And then you've got a 12 AA charger, which again is enough for 2 robots. And then in addition, we as Stephanie mentioned, the 12 pack. Oh, let's see. I never heard the 3 kilohertz tone. Okay. Well, let's go ahead and put in the speaker while we're at it. So I'll go ahead and take a little diversion here to sound. Okay, so there's a, what is it, Stephanie?
Oh, we got a thank you. That would probably help.
Yeah, I mean, we can go one of 2 ways. Since we all have microbit 2s, there's a built-in speaker and we could use that. But
The tutorial supports the original version, the 1.5 as well, so we didn't depend on it for this tutorial. And we
Yes.
skipped over this in our homeworks and our
Yeah, I took a little bit
So-
too long on some of the earlier stuff yesterday, so we ended, or on Wednesday, so we ended up skipping this. So let's do this now. There's not really too much review of advanced calculus and physics for this, so I'm sure you're all pretty well up on that anyway, right? A little bit of quantum mechanics. No, so basically the piezo speaker looks like, pardon me. The piezo speaker is a cylinder that's kind of wide and stout compared to the LEDs. And it comes in the package with the LEDs and push buttons. So these red LEDs and the push buttons, and then there was also that little piezo speaker inside it. And so let's see if we can give you a better close up of the piezo speaker. All right, there it is. It's got 2 short pins coming out of it. And in the tutorial, it says, hey, if your pins are, check the length of your pins. And if they're a particular length, of which this is it, you'll need to plug it in from underneath. There's a longer pin variety of piezo speaker that goes in on the top. But I can tell you that my kit has short pins, and I'm pretty sure that your kit does too. And so what you'll want to do is you'll want to set the robot on its side. And then basically, these are the 2 sockets where you plug in the piezo speaker. And so what you'll want to do is go in underneath and plug those pins in underneath. Oopsie, dropped the speaker. Try that again. Okay. So I have not pushed the speaker in all the way yet. I'm holding it against the little plastic header that comes out of the underside of the board. So find this little circle that says piezo on the top of the board. And then underneath, there's a little plastic header with a couple holes in it. And right now I've got the piezo speaker started in those holes. And looking for a good angle. Okay, so now I'm going to go and press it all the way in. There it is. So that's how to insert your piezo speaker with the short pins. And then the kind with the longer pins can just go in on top.
I think some kits do have the ones with the longer pins, and some are having no problems with them whatsoever.
Oh, excellent. Yeah. So basically, the longer, if you try to put the one with the shorter pins up top here, you can turn it upside down and it'll fall out. And then so the shorter pins you'll need to go in from the bottom. If you have, like I believe that the pins on these are 1/4 inch, and then the longer ones are about 3/8 of an inch. So if you have like 3/8 inch length pins, they should hold on up top. Okay.
And this just came up unexpectedly to us during the supply chain difficulties during the pandemic, when sometimes you order something from a supplier and you don't get exactly what you got the previous time, and don't necessarily get advance notice.
Yeah, and don't have a choice of returning it. Yeah, during the supply chain disruptions, beggars could not be choosers.
No, we were grateful to get them.
Yes. All right, let's see. In the robot shield with the Arduino Uno, we put the piezo speaker on the breadboard. True.
Mhm.
And we certainly prefer the longer pins for the breadboard too, but the shorter pins do work on the breadboard, thankfully. Okay, so let's talk about the tone call. Now, this is I think I want to show you. What's that? Oh,
That definitely gave me a tone.
oh. So yeah, now when you restart it, and there's some other fun stuff we can do with tones. Like here is a now I just want to show you the tutorial first.
We've got an it worked. For
Good,
another
good.
person. Good.
So here we show the piezo speaker with its actual part and then schematic symbol. And then we've got the placing the piezo speaker with a schematic of it, as well as identifying whether your leads are long or short. And then if you have the long leads, it goes into the top, otherwise goes underneath. And then once you've got it connected, it talks about the bot.tone method. And so here is our 3000 speaker vibrations per second for 1000 millisecond piece of code. And so this is the testing the piezo speaker, and it takes you through restarting the script to make sure that you know that it plays the tone every time the script starts. And that can help because, for example, if the robot is in the middle of a obstacle course, makes a sudden direction change, and then all of a sudden, you know, without a speaker tone at the start of the script, you might not know that its script unexpectedly restarted. And so it's a nice diagnostic tool for contests and whatnot. Save this by download project hex and then paste in the piezo speaker test to my editor and to you all, and flash that. Now, one of the things that Zoom does really well is filter out the sound that the piezo speaker makes. I might be able to hum at the same time it plays the note. So if I this is going to sound funny, but let's try it. I'm going to say ah. Hey, now it's not restarting. There we go. Okay, so could you hear the speaker over my voice by chance? No? That's amazing. Yeah, Zoom's got some pretty good filtering technology. It just kind of goes counter to the goal of the class. But as long as you can all hear that tone, that is great. And so it also goes from sound effects. It talks about musical notes. So here's kind of the range of musical notes that work pretty well in a piezo speaker. And so 1975, I believe, is going to be no, that's not a C note. That's B6. How funny. Yeah, when I wrote the earlier textbooks, I always used the C note. And so here is a very high speed happy birthday. First few notes from Happy Birthday, which thankfully is not protected under copyright anymore. I could not use that when I was writing books back in the 2000s. Chat. Paste. Okay, so there is a very brief Happy Birthday tune. So try that out, and it should be audible as Happy Birthday. And so now with that, we've got our piezo speakers working. And so I'll go ahead and fast forward and yes, now it should make a 3 kilohertz. That's 3,000 repetitions a second. So somewhere between the F sharp and the G note is where 3 kilohertz lies. And so next up, let's try the basic, or I'm gonna, I think I'll, no, I really don't want to skip the whisker style navigation, but I will adjust the code a little bit before before pasting it to you. I want to mention also that there's a some fluorescent lights can really cause trouble with robot infrared detection. And so the thing to do is to run this little script where instead of shining out light and looking for its reflection, it looks for a reflection without shining any light. So if a signal comes in that is confusing your infrared receivers, and sometimes that happens from fluorescent lights, you can end up with trouble with your infrared system. I'll go ahead and run that and just hit it with my TV remote. Slash. Okay, where'd my TV remote go? So we'll see, we should see these lights flicker here when I hit the receiver. It also makes a beeping sound, which again is probably going to be filtered out by the by Zoom. But you can hopefully see the lights as either on or flickering while I'm pressing the TV remote and then back off. Because again, these guys are TV remote receivers. Next up, we also have a detection range adjustment. A resistor resists the flow of electricity through a light emitting diode circuit. And by using a larger resistor, you can make the light dimmer. By using a smaller resistor, you can make the light brighter. And it actually guides students through testing the range of the infrared receiver. Pretty cool. Filling in a table. And then here is, I believe, the clunky navigation that, yeah. So this is actually, if you compare roaming with IR against roaming with whiskers, they are almost identical. The only code where it's really different is basically checking the infrared detectors instead of checking for the digital read on the whiskers. So, so I'll go ahead and before I paste this into you, though, I'm going to make the same adjustment that Dennis Pedersen made to make sure it backs up a little further and turns a little further. Dennis, go ahead and tell me if I'm doing it about right. I'm going to make them back up for 500 and maybe turn for 500 as well.
Yeah, I kept the turning the same, but back for 500 as well. So yeah.
Oh, okay. Well, how do you feel about the turning for 250?
I like it because the 500 turning gave me too much of a turn so that I don't feel like I get a good coverage of like if it's only a small object that it's trying to avoid.
Okay, sounds good. So I'm backing up for 500, but only turning for 250. Is that right? Oh, thumbs up. Thank you. And Okay, so now we're ready to run this. So go ahead and try this out, folks. It's pretty fun. But again, it's kind of a thing where you can add some different technology and then use some existing technology, that being the whiskers detection, and make an incremental improvement. Remember to put the switch in position 1 while you're loading the code, and then try it in position 2 once you've got the code running.
Here's a question. Would you recommend a switch case instead of the repeated ELIF?
Let's see here. Switch case. Let me check on something really quick. Normally I use switch case when there's a lot more options. When we have 3 or 4 options, I'm okay with ELIFs. I don't see a big difference there. Now, I guess the other thing is trying to remember. I'm looking up the usage.
May not be able to use switch case with logic and.
Well, that also is a really good point.
You need to switch on a single variable. Very good point, Nilu.
Yeah. So, and also in Pythonese, it looks like it's match. So I'm going to paste in the equivalent routine for Python. So it's match, and then you go with indented case and an action. All right. So next up, let's try some higher performance navigation. So instead of backing up and taking a lot of time to make a turn and then continuing to roam, you can basically do it on a much shorter sample interval, that being 20 milliseconds or a 50th of a second. Although with the code execution of the MicroPython interpreter, it actually probably pans out to considerably longer than every 20 milliseconds. So this again, this is all from the student workbook. We're down here in navigate and avoid obstacles, faster IR navigation. And I'll paste in that sample code. Ooh. Did something wrong. Bear with me. All right, there we go. So try that one out. It's a lot of fun. You'll need to replug in your microbit, reconnect it, and then hit flash and etc. I'm on my way to that right now. Connect. Flash. Okay. So then remember to unplug your microbit. By the way, as you're unplugging, I usually try to put my thumb on the back edge of the microbit to hold it into the socket as I unplug the USB cable. Otherwise, you could end up pulling out the microbit and having to plug that back in instead.
Question.
Yes.
Are we able to send programs via Bluetooth like MakeCode IDE?
Not presently. It's possible that you could, but I don't, I haven't done it, so I don't know the answer. I can look that up and see how it's working now. The last time I tested it wasn't working well for our purposes, but that may have changed. Especially with the microbit 2. I know that you can load stuff with Bluetooth. Whether or not it's compatible with having a third-party module like the Cyberbot module added to memory is one thing. Now, another thing is that we also do activities using that built-in Bluetooth radio as a networking device for our cybersecurity. And I'll be showing you the keyboard control and the tilt control in a few slides. And with those, I think that we need the Bluetooth radio for the remote control. And I'll tell you, the students get really excited about those applications. We had a tour group in the other day, and boy, they just loved those. So I'll show you those shortly. And again, those use the Bluetooth radio between microbits. And so, so I'm pretty sure that you can't use the Bluetooth radio for loading code and use the Bluetooth radio for networked microbit applications at the same time. Okay. Let's see. Now I hit an Easter egg somewhere. Yeah, here it is. Now before I paste you this code, I'll demo it first. And just watch what I do. So I'm going to take the example code. This example code is using a slightly more complex algorithm to follow objects using the infrared receivers by steadily making the LED light brighter. And so what I'm going to do first is connect and flash in the code after I reconnect my microbit. Okay, so now that my microbit is connected, I'll go ahead and flash it. And then I'm going to leave the button in, well, actually first I'm going to turn off power and make a slight circuit change. Let's see. So power off. Then I'll see if I can zoom in well enough so that you can see the change. Okay, so the change I'm going to be making is these two blue wires here. The reason they're blue is because this blue wire right here I'm gonna move it to the right 2 sockets. So it's gonna be plugged into D to A 1. Right there. And then I'm gonna take the other blue wire and move it over 2 sockets and plug it into D to A0. And what this is gonna do is it's gonna give the script the ability to take these infrared LEDs and make them progressively dimmer and repeatedly check the distances. So again, I'm just going to pull out this end of the wire that was connected to ground. And then I'm going to plug it into D to A1. Let's see, is that in the right spot? I believe it is. If I put this closer to the screen, yeah. Now you can see that the wire to the right infrared LED is being plugged into D to A1. So I'm plugging that in. Then the left infrared LED, the one all the way over here, it has a blue wire also going to ground. And so I'm going to unplug that and plug it into D to A0. So the closer infrared receiver, or no, the closer infrared LED, it's got a wire that went to ground and we're plugging it into D to A1. The infrared LED that's further on the other side of the breadboard over here, we're going to take its wire and that's connected to its cathode, the shorter pin, and plug it into D to A0. After you've done that, set the power to 1 with the script on. And what you'll see and my
We can see.
okay. What you will hopefully see is if you have nothing in front of the robot, you'll see 2 solid bars. And then when you take an obstacle, put it in front of the robot, what you'll want to do is put it close enough so that one of the bars has either disappeared or is less than the middle, and the other bar, and this might be the right bar for you, for me it's the left, the bar for the left receiver, is sitting right about in the middle. And then my right bar has disappeared. Now, get one of the, set the distance of the robot so that one of the bars is right in the middle, like here. Oh, sorry, you can't see that. I'll repeat. Okay, so as I get closer, all the indicator lights go away. Or, yeah, there they are. They're all gone. We're too close. And as I back up further and further and further, you'll see some more lights here. And back it up until you get 3 lights on one side. And then either fewer or no lights on the other side. Oops. Okay, so then the last thing I'm going to do is where we don't see lights, that's because this receiver is too sensitive. So I'm just going to bend the little receiver to make it look downward until I get the lights matched up here. So I'm looking downward at about 45 degrees. And that actually made it a little bit. Okay, so now that I've got them matched up, watch what happens when I set the power to 2. Okay, so it is actually tracking the box. And so if I move the box around this way, it's still looking at the box. And it very faithfully tracks the box. And the main thing though is that you've got to have the receivers nicely matched up for this to work. All right, so with that said, I'm going to paste you the script. We're going to have you guys try this. Oopsie. Oh yeah, that's right. This should work. And paste. There we go. All right, so there's the script. And as you're loading the script, I'm going to go through the calibration one more time. So I'll straighten out my oversensitive receiver there. And then what I'm going to do is use my Cyberbot box.
We're getting an error reported. I put your code into the editor, lines 42 and 47. Gives us error message, operator plus equals not supported for this combination of types.
Let me guess, you're in version 3 of the editor.
Thumbs up.
Yeah. So that's a pre-compiler. It's a bug in the editor. But don't worry, if you run it, it'll work fine. It's not quite smart enough to deal with it has a virtual MicroPython engine inside the editor because it does, the version 3 does simulations of the microbit, but it's not quite ready to deal with the Cyberbot module yet.
And we got another thumbs up there.
Awesome. Awesome. Okay, so again, you probably won't have perfectly matched infrared receivers. If you do, great. If you're able to back up your robot from the box so that both of the bars here show 3 lights on at the same time, then you don't need to make any adjustments. Here, I backed mine up, so I have 3 lights on one side and only 1 light on the other. So this side is more sensitive. It thinks that the box is nearer right now. And so I'm going to bend this receiver downward to make it look down. And for me, it was about 45 degrees. And now that I've got the receiver looking down at 45 degrees, might be able to see it right there. See if I can give you a better view. Yeah, there we go. See, got one receiver looking straight ahead, the other's looking down at about 45 degrees. And for me, that's how far I needed to make it look down in order to match up these 2 distance detection indicator bars. And once I've got those 2 matched up, then I can go ahead and turn my power on, and oh, lo and behold, I did something wrong.
Well, Randy's confirming it works.
Okay, good job, Randy. Excellent job, Randy. Yeah, and mine now works. I don't know why it was confused for a little while, but I think it had to do with just that it was running the code, and it may have taken a few repetitions to get caught up to reality when I turn the power on all the way. But what's fun about this is that it's very, very sensitive. It for example, you know, when I back the box away from it, it comes forward. When I push the box toward it, it backs up. And I can even rotate the box. And hopefully you can see the robot has rotated too.
Can the sensitivity be adjusted via code?
Yes, as a matter of fact, I significantly reduced the sensitivity. So maximum sensitivity. There's two ways to do it. So the overall sensitivity, I wanted it following closer than it was. And so what I did was instead of 38,000, so that's the optimal, most sensitive, makes it really far-sighted. You can adjust the sensitivity by changing out resistors, which was an earlier resistors with the infrared LEDs to make them brighter or dimmer. But another thing you can do is it is supposed to be flashing at 38 kilohertz or 38,000 times a second. This is flashing at 39,500. So it's not the optimal frequency. It's a little off from that. And what that does is it makes the whole system less sensitive. It makes the thing follow overall closer. Now, you can also, instead of bending those infrared receivers down, I could have made the right side dimmer here, but I just felt like it was going to be, more time consuming, go back and forth and set it up in code to make the left and or right receivers dimmer. So again, I made the infrared receivers less sensitive by using 39,500 as the flashing rate instead of 38,000. And then instead of making the light dim in the script, I just bent one of the receivers downward.
We have a comment and a hand up.
Okay, so
The hand up, the comment is, it doesn't seem to sense dark, semi-shiny objects, my phone on my desk, but it completely senses my hand. So,
a
yes.
very astute comment, yes.
Yep, and it's surprising, black surfaces and matte finished surfaces tend to absorb the infrared light, though there is some variations there. The black ink used to print on shiny photograph paper is very shiny. Black velvet is very shiny to infrared light. And we figured this all out the hard way through various years at Parallax. It can be a fun activity with the students to get a bunch of different surfaces and see how far away or close they have to be to get any kind of reflectivity. And you'd be surprised.
Yeah, and so just on that note, also, another thing that we do in the infrared chapter is the drop-off detector,
Oh, yes.
which is looking. Now, we don't recommend, don't try this at home.
There was a hand up before you get too deep into that.
Oh, okay.
Kathy had a hand
Sorry,
up.
go ahead. Okay,
And
Kathy, what is your question?
I think I figured it out.
oh,
I'm obviously on the version 3 too.
Oh.
3 also. And I think I figured it out though, because it seems to be running now.
Okay, yeah, the main thing is it's going to warn you that there is a problem because the built-in runtime simulator in the version 3 editor doesn't understand what the infrared is returning.
Yes. So I notice on the code though that quite often there's an orange dot to the left of the number line.
Mm-hmm.
And then everything on that line or some of the things on that line are underlined with a little squiggly red, which
Yeah, it's telling you there's a syntax error as far as it knows. And
okay, even though it was copied and pasted exactly.
Yeah, and again, it's because the runtime simulator in the editor is not ready to deal with the Cyberbot module. It's a little bit beyond what the Microbit Education Foundation normally does with their microbits.
Okay,
and so
great. Thank you.
You're welcome. I'll ping them about that again because we've discussed that before. So here is the Cyberbot, and it's on a tabletop, and it's avoiding the edge of the tabletop. What I like to do is there's like 8-inch wide strips of marine tape that you can get at hardware stores like Lowe's and Home Depot. It's like electrical tape, but it's about 8 inches wide, and you can get that and then put it on some largish mats and like a white poster board. And you can make an obstacle course. And actually the fast IR roaming, the one where we avoided obstacles with a tight loop, the faster IR navigation here, this one, you can actually make a track and have it follow this. So I'll paste that in. And I've been holding on to you guys for too long. Let's take a 7-minute break. It's 11, so we'll see you at 18 past the hour.
And I'm going to pause the recording.
We won't have time. All right, so we won't have time for it today. Welcome back, everyone. But I wanted to show you at least, actually, we have a lot more applications. What I did, or what we've done during this workshop is mainly gone through some of the key places where students might need help. I've talked about a number of things like how to save a .hex file instead of a .py file, how to adjust your infrared receivers, what to do if you see that your servo has a sticker over the spot where previously we used to have a hole for adjusting the servo, and those kind of things. So I focused on that. And then we did a couple of applications too. We did whiskers, where it's a contact sensor, and we first built the whiskers, then we tested the whiskers, and then we started using robot applications. And then for homework, you built the infrared circuit, you tested the infrared circuit, and then today we tried some robot applications with it. Now the same routine, and that's always a really important habit that we try to get everybody into, because doing a little bit at a time and testing between each step is much better than building a house of cards and having it fall over on you because of a mistake made earlier on. So we also have visible light in the individual robot kit, and it's got a nice little film at the beginning, or film clip at the beginning of it, where basically the robot's entering the picture, and it has a couple of light sensors on the front of it, and as it's making its way in, it's currently going about this away. And as soon as the flashlight turns on, it's going to change its direction and go the other direction. And it follows a flashlight, or even your cell phone flashlight, pretty well. With the cell phone flashlight, you have to get kind of close to it. There's a lot of information in this chapter. For example, we talk about, we introduce the phototransistor as a kind of transistor where with more light, it lets more current pass through it. With less light, it lets less current pass through it. And then by connecting a resistor to it, it so happens that with a resistor, when there's more current passing through it, which is done by more light on the transistor, the voltage across this thing will be higher, and with less light, there will be less current, and the voltage across this resistor will be lower. And this A to D2 socket will measure that voltage. And we even do a little bit of Ohm's law, voltage equals current times resistance calculations, and it actually converts the native 1024 level. So 0 to 1024 is equivalent to 3.3 volts, and so we use 3.3 over, or 0 to 1023, pardon me. And so 3.3 over 1024 is used because there's actually an empty slot up top. So the 1024 is the correct thing to divide by in this case, as opposed to 1023, because 1023 is the highest number you can get. And what that indicates is that it's just a smidge below 3.3 volts. It's not quite there yet. That's the highest you can get out of a let's see, we can use the map function to do this too. Now the map function, let's see, I know I wrote a map function and I put it in a potentiometer, or no, I put it in, let me see if I can look that up here real quick. Drive. Because to my knowledge, there's not a built-in map function in the microbit. Please correct me if I'm wrong on that. To my knowledge, you have to write a map function. And so I'm looking one up for you.
We have a quote from Dennis. First, you tell me that an LED is also a light sensor. What next? A speaker is also a microphone.
Of course it is. That's funny, Dennis. You're right.
And-
Yeah,
and-
so we've got a generator and a motor. We've got a LED light emitter / sensor, and now yes, a microphone can also be a
And Nilu's mentioning, sorry, the map was for the Arduino. I think.
but you know
it's-
what, Nilu, we have a map function. I'm just looking for, oh, darn it. Let's see. I just clicked the wrong thing and left my search. I'll paste a map function in. Potentiometer. Okay, so what I'm bringing up here is the almost ready for publishing. It's the electronics kit. This is an example of the electronics kit that uses the microbit. It's called the What's a Microcontroller kit. And hopefully 150 will be a good number. And so, so partway into the textbook. Yes, Stephanie?
Oh, there's tornadoes breaking out all over the Midwest that are affecting some of our attendees, and we're just hearing that somebody's safe, so I'm just relieved.
Yeah.
You're missing
oh.
all the drama in the chat.
Yeah, I apologize for that. I'm just kind of obliviously rattling on in our, obscenely nice weather. Sorry about that, Midwest folks. Okay, so I'll get you a map function in just a minute here. I'm going to have to do a Control F because I don't remember where it is. Map. Okay, so that's the first instance of map. Okay, here is the mapping function. Okay, so for many of you, this won't matter, but there's a map function where you can say, hey, if you have a sensor that has this range of values, but you want to map it to a motor that has that range of values, instead of using y equals mx plus b, which we do a lot of in this electronics book, you can also simply use a generic solution to y equals mx plus b, which is called the map function. And I just went ahead and pasted an example script. Now, this example script is not going to work for you because we don't have a potentiometer in this kit, but I want to show you just note this map function right here. In fact, I'll just paste that in. So this is basically if you don't want your students doing any kind of y equals mx plus b calculations to figure out, gee, I have this range of inputs and I need that range of outputs from the measurement. They can use y equals mx plus b, or they can use this map function, which is something that the Arduino has built into it. So save that if you like. It might help out your students at some point. So here is the light sensor, and let's see, I was talking about Ohm's law, And so we're doing, and yes, you could use the map function for this. You could say, hey, I have an input range of 0 to 1023, and I have an output range of 0 to 3.3. And then we'll call the map function and it'll take whatever our measurement is and give us back the volts. So that's you could use the map function as opposed to just using some math and saying, hey, here's my measurement multiplied by this fraction to get from something from 0 to 1023 to something that's just under 3.3 volts. And then there's a park in the dark activity that's kind of fun using that sensor. One of the things that students find out is that it's kind of a challenge to get it calibrated for their lighting conditions. And they may even have to use a different resistor in this circuit. So back to this photo transistor circuit here, 2 kilo ohms. If you've got a really bright room, might need to be 1 kilo ohm, maybe even 470 ohms. If you've got a really dark room, you might need 10 kilo ohms, 10,000 ohms. So this resistor value, depending on the ambient brightness, is something that students will find in some cases that they have to change in order to get to the robot to park when it gets into a shoebox. Next up is there's another way of measuring light, and I went to the wrong spot. Okay, after that circuit where the students have to replace a resistor in order to make it the right sensitivity for their ambient light, we introduced the capacitor. The capacitor is like a very small battery that you can charge up, and its charge lives for a very short amount of time. There's much more scientific explanations of it, but for for the sake of our workshop right now, we'll leave it at that. But you can also read more in the text. And what we do is we build a pair of circuits where there's a capacitor in parallel with the photo transistor. And again, this is just a light controlled electric current valve that more light, more current, less light, less current. And so this is what it looks like on the robot. You've got both of them sort of pointing outward. And then basically what happens is the script, first of all, turns P8 on. So it's applying 3.3 volts to the circuit. And as it does so, electrons rush into this plate, and electrons migrate away from that plate. And so it's storing some charge, and you can measure 3 volts across it. Then what the script does is it makes P8 an input. So it's like sensing a button press. And as such, it looks invisible to the circuit. And so the circuit is completely changed. It's like you just disconnected your power source of 3 volts from the circuit. And what happens then is no current can go this way anymore. And so what happens when this disappears is that the capacitor drains through this current valve. And the rate at which it drains is controlled by how much light is shining on it. And so if it's really bright, the capacitor loses its charge quickly. If it's really dim, it loses its charge slowly. And the Cyberbot is able to measure that rate. And then by measuring it, and a QT circuit is a more general term of a RC circuit, for those of you who know the electronics this is based on. Charge time circuit, or a charge transfer circuit, encompasses both, if you had a resistor here with a capacitor, but it also encompasses a phototransistor circuit, which behaves a little bit differently from if you had a variable resistor here. We used to have photoresistors, but let's see here. Cadmium sulfide, I think it was, got on the naughty list of the ROHS restrictions on hazardous substances rules back in the early 2000s. So we had to switch to a phototransistor. And there's some fun stuff like testing the photosensitive eyes. And so they get to see in their terminal the left and the right values of this decay measurement. And it talks about how the capacitor's voltage decays as it delivers current through the phototransistor, and how this can go fast or slow. So here's bright light with fast decay and dim light with slower decay. And then it talks about the math to measure this and compare the two. So that it's called a normalized differential measurement, where you add the two light measurements and then you divide them into one of the two, and then you can tell how far toward the right or left the measurement is. And then basically that you might be in a dim room or a bright room, but you've always got this ratio here. And so you'll always be able to tell when something's brighter or dimmer, and you'll get a nice strong response. If you use some absolute values for left and right, it doesn't work so well. And then so we even do a little graphic display. So you can see on the microbit whether the light is shining towards the left or the right. Brighter on the far right, for example, would have your little spot over here, and then it navigates by the right. And then we do navigation after all that testing. So that's just an overview of the light sensors. And then what I'd also like to talk to you about is if you have a classroom full of microbits, you can pair off the students, and they have a lot of fun with these kind of activities where the Cyberbot is on a microbit radio network. This microbit radio network was also created partially for creating the need for cybersecurity measures, because attacks on the network can disable the ability to control your robot. And so here is one of the microbit networked applications. Okay, bear with me while I get this zoomed out a little bit. Okay, so what we have here are 20 robots, roughly a good sized classroom. And then there's one microbit connected to the computer over here. So this one microbit is going to take input that's typed into the computer terminal, and it's going to transmit that out over its Bluetooth radio, not using Bluetooth itself, because Bluetooth you have to pair up, but it's using the Bluetooth radio, but a protocol by Nordic Semiconductor that makes the microcontroller and the microbit. And it's using that Gazelle protocol, and it's transmitting out on an open connection to all these Cyberbot robots. And so here Ken Gracie he's typing in 100 for the left speed, 100 for the right speed, and some number, I forget what it's going to be for the runtime. That was 100, negative 100, and 500 milliseconds. You may not have been able to see it, but so this should go forward for half a second. And there it went. And so he's currently orchestrating all these different kinds of maneuvers with his computer connected to one microbit. And that one microbit is sending it out to all these robots. Pretty cool, huh? Okay, so this is keyboard control. Now, the keyboard control chapter actually starts you out with a tethered version, and then it jumps to the radio control. So we're first using the keyboard to send over USB to the microbit, and then we're using the radio as you saw in the video. Now, another one that's pretty cool, and again, this has two purposes. One, it's a great way to pair students off and have them do something fun. That you don't have to use just a microbit. You can have just a microbit, or you can use two cyberbots. One is a tilt controller, and the other is the tilt controlled cyberbot. And let's see if I can get this video running. So watch carefully. You'll hopefully see a little LED display that shows essentially which way is being tilted down. So it's where, if you put a ball bearing in the center, which way would it roll off of the microbit? And you'll see actually that since this microbit is using its radio to transmit to the microbit on the cyberbot, and again, this could just be another cyberbot, it'll mirror the tilt that's being done with this microbit. I'll play that one more time. It's very responsive. I've seen a lot of SumoBot competitions done with just plain old cyberbot robots. Of course, it's not, it's not going to be like a proper sumo bot, but if I brought a ring out the other day, and a group of students were visiting, and they had a lot of fun trying to knock each other out of the ring with this configuration. Now this is a pretty significant chapter. It goes very much in detail on the accelerometer, which is the tilt sensor inside the microbit. It talks about the trigonometry behind figuring out how far you've rotated the microbit and in what direction. And then it goes into doing the display of the direction you're tilting over the radio. And then at the very end, there's the actual application. So one thing you can do is, if you're short on time, you can just have him jump to the end and do the last activity, which is the application itself. It's got the scripts for both the transmitter and the receiver robots. So here's the tilt controlled cyberbot code and the tilt controller code. So if you're short on time, just have your students jump to the end. If you have the time and the inclination to get students into some geometry, some trigonometry, some basic math, some physics about gravity and the forces exerted by gravity, and how they resemble the force you feel when you're accelerating, there's lots of good material here. By the way, was everybody able to see both those videos well enough? Do you want me to replay any of them, or are you okay as far as, okay, I got one thumbs up, two, okay, good. So, all right, so next up, I wanted to show you a little bit about cybersecurity. It's a little bit of a dry topic, but there is an incredible market for cybersecurity in this day and age. And so students graduating with experience in cybersecurity will be at an advantage, and also imparting an interest in cybersecurity and just an improved understanding of it can have a lot of good outcomes. So if we look at the CyberBot tutorial series, and I left out the projects here. I'll be talking about the project shortly anyway. We've got some basics here. And usually, if you're just doing what we went through, all you need to do is talk about these first three, really: the software, the writing microbit programs, adding modules to your microbit, and there was also the saving your microbit scripts and reopening them. So those first four are enough to get us through all of what we went through. And all of what we went through also reinforces a lot of the basics that were that came with writing microbit programs. Now, there's also computer microbit talk. That's where you're using a terminal to either enter statements that your microbit executes or run applications like a countdown timer, which is a kind of a classical application that, you know, everybody's familiar with. There's also some computer sciencey stuff about dictionaries, exception handling, and strings and characters. And for the cybersecurity part, computer microbit talk, dictionary primer, exception handling, and strings and characters all become very important background lessons. So the first set of lessons, the computer science basis for cybersecurity, is here in the latter half of the prerequisites. These are not required for doing all the activities we just did, but they are required to understand what's going on with the cybersecurity. Then, sorry, jumping around here. Then infrared light navigation is here. Gosh, I should just be showing you this on the page. Okay, so here in prerequisites, we've got set up, how to save, writing microbit programs. That's where all the basics are. And then computer microbit talk is where we start the cybersecurity foundations. And then all the rest of this, pardon me, computer microbit talk, dictionary primer, exception handling, strings and characters. Those are there because they're needed for the cybersecurity lessons. Now, in the main lessons, there is a networking basics set of chapters, and that's going to be radio basics, radio data, keyboard control, which you just saw the video of, and tilt control, which you just saw the video of. And what these do is we set up our little network and show some networked applications here. Like in here, there's a chat application where students realize that they want to go off on different channels, but they also want to have their communications private. And so that gives a good reason to learn some of the cybersecurity coming up. We've also got the countdown timer here for a microbit only version of the cybersecurity. And then we have the tilt control and the keyboard control, because those are applications that we'll want to protect too. Then we get to cybersecurity proper, where we start out with encryption. And this is not a professional grade cybersecurity set of lessons. It's more of a get familiar with cybersecurity and also reinforce some of the computer science concepts that are underneath it. And so we start off with a Caesar cipher and encrypting stuff by hand. And so pick a letter, count over a certain number of letters, and use that letter in your message. And so your plain text hello becomes in ciphertext MJQQT. If your key is 5, that means you're counting over 5 characters to encrypt, and counting the other direction, 5 characters to decrypt. And then we show how to do that with scripts. And by the end, we're getting into some ASCII characters. So any printable character, they get a function to start with. And then they also learn about some of the other ciphers, the simple ones at any rate. And then we've got sniffing attacks and defenses. So essentially applications, either microbit only, like sharing some emoji, or chatting, or applications like the countdown timer, but over the radio. And then let's see, and then using encryption to foil the ability to quietly monitor any of the information that's getting transmitted and received. Then we have brute force attacks and defenses, and it shows how, especially how scripts can end up doing something equivalent to trying all the different combinations on a combination lock. And going back to the key that was used earlier to decide how many characters to count to the left or right to pick out new characters. So there's activities in here on how to crack a cipher with brute force. And so there's an actual script that is used based on the assumption that we are using the Caesar cipher. And so happy becomes, you know, some group of characters. And then in a brute force attack, we actually go through all the possibilities and then find something that's human discernible to take a guess that the key in this case is -22. And then we have let's see, brute force attacks and sniffing. And then let me open up the draft that we're in the process of publishing. Let's see, it's malformed. So here is a little preview of malformed packet attacks and defenses. And it's using all that same, it's using all the same same reasons for wanting to protect your network. So all the network stuff that was learned with the keyboard controlled robot and the tilt controlled robot and sharing emoji and chatting. No, not chatting. So sharing emoji is one of them. And the countdown timer is the first one. And we show how the countdown timer works just fine until you modify the script to send it a malformed packet, and then it stops dead in its tracks. Now, the same thing happens with sharing emoji, that basically when you run a script to share emoji, and in this case, we share an X, a check for no, and a check mark for yes, and forget what else we share. But anyway, there's several different, I think a heart. And so you can use the buttons, the A button to pick your emoji and the B button to transmit it, and it goes back and forth. But when somebody picks the, using a modified script, when somebody picks the skull emoji and hits send, basically it stops the microbit in its tracks. It causes an exception, an unhandled exception. And so the way to fix that is to use exception handling, which was introduced in the computer science part. We also do one with the Cyberbot where there's keyboard control, and the modified script has a little thing where it sends a malformed packet and the robot stops in its tracks and it won't do anything. It becomes unresponsive if you send it a negative time value. And it again has an unhandled exception. And so students can learn that in their robotics contest, if somebody else is interfering and sending malformed packets, their robot just stops. And if they're not allowed to run in and restart it, well, they're out of luck. So, so this is an example of something where there's an incentive to protect your robot network, in this case from malformed packets, hardening against that. And that's kind of an overview of cybersecurity with the Cyberbot. So there's lots more chapters available and things that you can do. And so keep that in mind. The Cyberbot has just great potential in terms of fun stuff like tilt control and radio networked robots. And then, of course, the cybersecurity lessons. There is also a cybersecurity only or a microbit only version. So this has, for the most part, the robotics stuff removed from it. It's just the portions where you're primarily using the microbit on its own. And there's a couple spots in here where it says, hey, if you have the robot, you know, you can also try this. And but if you don't, just skip it and you can use the microbit on its own. I think it's more fun with the robot personally. And then wanted to talk about what it's going to look like when I send out the final email saying, hey, thanks for coming, everyone. I'll send a link to a page that looks like this. This is the cybersecurity one. And oh, actually, so there's two reasons I want to talk about it. First of all, if you want to look at one of the recent cybersecurity ones, here is a video from late August of 2022. And so there's 3 2-hour video sessions, and you can do an at your own pace version. And the slideshow is right down here at the bottom. You can also keep an eye out on cybersecurity workshops coming up, but know that you can do the at your own pace using the recorded videos from our last cybersecurity workshop. And so I'm going to skip all these slides about cybersecurity. It's mainly stuff like just reinforcing, hey, here's encryption by hand, and then encryption with a script, using some of the string stuff from the so you can go back if you want to and look at these on their own. For example, dictionaries, which is key value pairs, which has to do with how stuff gets transferred across the internet. And so very quickly, talk about the projects. If you buy a robot on its own, these are sold separately items. If you get the robot with the in the form of the class pack, these extra parts are included for a turret with a rotating ultrasonic distance sensor, a little line sensor, and a TV remote. And so we have projects documented. So here's the one for the QTI line follower. And so like if you click this tile, you can actually follow the link. And so here's the QTI line follower stuff. And then you can go back to the Cyberbot tutorial series and also see that the QTI roaming with ping, and this appears at the bottom. So these 3 are documenting those 3 sensors that come with the class pack. And then this is the recently added Feedback 360 servos that have built-in encoders, so they know how far they've turned, and you get better speed control, higher speed options, and the ability to go specific distances.
And I have just put in the link to the Cyberbots section of our web store, so you can find the kits and the compatible add-ons and maintenance parts easily, all in one place.
Thank you very much for that, Stephanie. I think I have a slide for that coming up, but in case yes, I see it down, or I see where it's starting down there. All right, so a couple of wrap up items, like here's a link to the rotating turret. I also, just for fun, included a link to the gripper. It's kind of fun to see how this thing works, except for so this is a different robot, but we have it set up to work on all our small robots. This one is the activity bot where the course starts in early May, but this is not part of it. This is just an optional add-on for any of the 2-wheeled tail dragger robots. And this is one I don't think it's supported on the microbit, but it's kind of a cool little color sensor. Electronics lessons I mentioned earlier. One of the cool things about the electronics lessons is that there's a built-in, there's a web oscilloscope and a web multimeter that uses measurements that the microbit takes. So, so like if we look at, so here we are. Here is the web voltmeter, and as you probe the circuit, it shows you the voltage across it. And as you probe a part of the circuit, it shows you the voltage across that. And if you probe another part, it shows you the voltage across that. And it so happens that those two voltages add up to the total voltage across the circuit. And we talk about some of the theory behind that. It's called Kirchhoff's voltage law. We also have resistance, measurement units, and et cetera, lots of good stuff. Then later on, when we get to signals like the one to control a servo, and this is a slightly different kind of servo from what you have. It's actually the original servo design, where based on a given signal, it holds a particular angle. So if you give it a 1 millisecond signal, it holds 0 degrees, 1.5, 90 degrees, 2.5 milliseconds is 180 degrees. And again, this is the amount of time a light would stay on. And what we have near the end of the chapter is the ability to measure it. And then what we do is we use the web oscilloscope to actually measure the those brief on signals, and it helps understand how pulse control works. And they actually use the oscilloscope to zoom in and take finer measurements on how long the pulse lasts as they see the servo turn to new positions. Oh, it's already 5 o'clock. I got to get you guys out of here. All right. Very quickly then, educational resources. When you go to learn.parallax.com, you can go to educators. And then if you go to Cyberbot resources, for example, and you have not logged in, what you're going to see is this locked up stuff. There is some general publicly available to teachers, not very interesting to student stuff, but then the logged in part is where you'll want to follow the login link. And I'll take this off screen and log in real quick. Let's see here. Okay. Okay, so I just finished logging in and coming back here and following Cyberbot resources. What we have now is, instead of a locked box, we have this assessment material. This is summative assessment. Let's see here. So let's take a look, for example, at the touch navigation. It downloads as a zip. I'll show that in Finder and then unzip it, which you can also do in Windows. And then they offer a PDF and an RTF. So the PDF is for Adobe Acrobat Reader, or you can drop it in a web page like I just did. And then the RTF is for Microsoft Office. And so here's an example of one of the worksheets that comes with it, and then it has solutions. Careful not to give these to the students. It's right at the tail end of the document after the worksheet. Now, just a reminder, the student lessons are at learn.parallax.com. Oopsie, sorry about that. Student lessons are at learn.parallax.com. Teacher resources are when you hit the educators tab up top. Reminder that there's a lot more microbit only fun stuff in this YouTube 2-hour session. The first one of 2 is, I think, where most of the good stuff is. Reminder that as a warm-up, you can use the Make It Code It site to do lots of fun projects with your students to get them excited about the microbit, or as a precursor to the robotic stuff. There's also documentation. I included a link. Now, another place where there's lots of free resources, including for the Cyberbot and the microbit. We've got some computer science and cybersecurity stuff for the microbit on its own. And then there's Cyberbot resources, and they are at cyber.org. This is for teachers who teach in the United States. And if you're not already, if you don't already have an account to access their curriculum, you can just go ahead and hit the sign up button and make sure to use your school email address so they can check you as faculty, and then they'll send you orientation on their resources, and I can help you find some of that. But Coding Fundamentals is the one where there's microbit programming, there's computer science, there's cybersecurity, and then cyber literacy 1 and 2 are where you'll find the their Cyberbot resources. These slides are outdated. I don't want to be showing you potentially incorrect prices. Stephanie posted in a link, which I'll instead follow. So these are the, this is the link of all things Cyberbot. So that includes the 12-pack for classrooms, as well as the individual kit. And you'll further on, you'll see some optional add-ons like the gripper kit. So that's where to find Cyberbot stuff. There's also a microbit category along the left. You can also, there's a conversion kit therein where you can convert either a BowBot or a ShieldBot to a Cyberbot. And one nice thing is, once you have the microbit and the Cyberbot board, you can just unscrew 4 screws and disconnect the servos and take the Arduino board off and put the Cyberbot board on if you're teaching different classes. Here is a general info page. I forgot to put the link in there. I don't know, Stephanie, if you can help me with that link. Paste it in. Upcoming workshops we talked about. Quick reminder to unplug the barrel jack when your Cyberbot is not in use. This slide has all the ways to get a hold of us. This email here, education@parallax.com. I can't recommend this one highly enough. When you send a question or comment to education@parallax.com, those of us who are involved in the educational documentation and product development, I'll see it. If it's a question, the most appropriate person will get back to you. And if it's a comment, we'll also probably get back to you, but we'll take it to heart and see how we can make it better to help you do your job better, or make it easier to do your job, whatever improvement we can affect. Thanks a lot for coming. Cyber.org, which was our partner in developing the Cyberbot, thanks you for coming as well. And we are Parallax, and we'll look forward to hopefully seeing you at another workshop. thanks for coming to this one. And we'll go ahead and continue the discussion and do any tech support that you might want before we end the workshop. But this is the end of the recorded part. Thanks again for coming and have a great weekend, everyone.